Hey Srinivas, how are you? Srinivas, are you there?
Yes, sir. I'm fine, sir. How are you, sir?
Good, good. How is everything? You are working in this college, is it? Or you joined this meeting?
Yes, sir.
You are working in this college or you joined this meeting?
No, sir. I'm working in this college only, sir.
Oh, is it? Okay.
Hello, sir.
Yeah,
Sir, I will call you in the evening.
yeah.
Okay, sir. Thank you.
Gajendra sir,
Yeah. Shall we start?
this is Parthasarthi from EC department VVIT.
Oh, okay. Hi.
Yeah, shall
Please
we
tell me.
start, sir?
Yeah, you are wish. I'm ready. Yeah, if everyone joined, then we can start. Some people are expected, then we can wait for a few minutes. No problem.
Okay, we wait for 2 more minutes, sir. Then we
Sure.
start.
No problem.
Sir, with your permission, I will start, sir.
Please start. Please start.
Yeah. Thank you, sir. A very good afternoon to one and all. Welcome to session for STTP entitled Mixed Signal Design. The topic of today's session is mixed signal circuit design for ultra low power applications. We are fortunate to have an eminent personality as our resource person, Gajendra Chowdary, Dr. Gajendra Chowdary, working as professor in IIT Hyderabad. He did his BTech from Usmania University, MTech as well as PhD he has completed from Indian Institute of Technology, Delhi. He has a rich experience in industry also. While he is pursuing his research, he worked at ST Ericsson from 2008 to 2011, and then Aura Semiconductor during 2013 to 2017. His research interests are including analog and mixed signal circuit design for ultra low power applications. And his contributions to the field can be understood looking at his publications. And you can see at the very young age, he has a prominent number of publications in IEEE transactions. Also, he is having one US patent. And as I have been informed, today is along with another resource person, actually she is his student only, Miss Priya, who has recently submitted her thesis on the same field. He did his BTech in Electronics and Communication Engineering from Anna University, and she worked as VLSI design engineer in Hyderabad. Her research interests are, this is thesis. The title of her thesis is CMOS circuit design techniques for microscale thermal energy scavenging. And she recently submitted and is awaiting for completing her viva voice. Her research interests are power management circuits and design efficiency, design of energy efficient low power integrated circuits and systems. Sir, welcome to this session, sir. Now stage is yours.
Okay, thank you. Thank you for the introduction. Yeah, she will speak tomorrow. Today I'll cover some topics, and she'll cover some more topics tomorrow.
Okay, sir.
So how many are registered for this course total?
Sir, total 110 members, sir.
Now 110 members are there in this call, huh?
No, sir. Actually, total 110 registered. They are adding slow by after 10 or 15 minutes. Then.
Oh, okay,
Total number of participants are 110 registered.
Oh, they are from your college or across the India?
No, so across India, sir. Across India, other states also so many participants is there, sir.
Okay. Thank you. So shall we start now, or we shall wait? Can start, right?
Okay, you can start, sir.
Okay. See, yeah. My voice is clear, right? You are able to hear me clearly?
Yes, sir. Yes,
okay.
Sir.
Thank you. I have fixed a camera here. I hope you can see a whiteboard on my screen. You can't see, is it? Okay.
Not visible, sir.
Yeah, I understand why. 1 second. Obviously. Can you see a board? If needed, I'll use that board. That's why I just wanted.
Yes, sir.
Okay. Okay, so let me start. Can you see my screen?
Yes, sir. It's
Yes, sir.
visible, sir.
Okay, thank you. Yeah, see, there is no end to topic what I'm talking, but I'll try to cover some things. I hope that's okay. Okay. So do you see a block diagram on the screen?
Yes, sir.
Okay. So the objective of this presentation is to let you know some of these circuits which can be used to build very low power mixed signal and analog systems. So I'm showing an example system here which we built. So this system, what it does is, it basically monitors the temperature. It's a teeny device of 1 centimeter square PCB it's built on, which is supposed to monitor the temperature every half an hour or 1 hour once and store it in the memory. Whenever the user wants the temperature, it basically sends them to a radio channel. So I repeat. So this system is very small, tiny system, which basically monitors the temperature. And every 1 hour once, it basically radiates all the temperatures it has stored whenever the user asks. Now, this whole system doesn't have any power. This 1 centimeter square PCB is mounted with a very teeny solar cell. It harvests the energy from the very low intensity light. And even in a deep dark room, it can just get some packets of energy and charge a very small battery, teeny battery. It can be a battery, it can be a capacitor. And whenever there is enough, every 1 hour, it basically turns on this temperature sensor. It takes the temperature reading, converts into digital, and stores it in the memory. And whenever user wants, it basically user sends a reference clock at 50 megahertz. The system basically doesn't have any local crystal oscillator. So it basically tunes to the frequency what is being sent by the user, and it locks to that frequency, and it radiates all the data it collected back at 2.4 gigahertz. So this is the whole system. Now to build this system, the available power can be sometimes very small, going tens of nanowatts to tens of microwatts. So even when the power is really small, how do you make sure you do some operations is the objective. So to build any system like this, we need three things. One is a reference voltage, another is a reference current, another is a reference oscillator. So any electronic system to build, you need these three things. Along with the supply and ground battery, you have to build these circuits. These are like voltage reference, current reference, and an oscillator. So you use these three circuits and as a reference to build the complete system. For example, if I want to build an ADC, I need a reference voltage and a reference current, and I need a clock to run the whole system. So these are the blocks which continuously consume power in the entire system. So remaining all blocks may not consume power. They see, for example, there is a temperature sensor. The temperature sensor will turn on only once in a while, maybe every 1 hour, few milliseconds or microseconds will turn on. Rest of the time it is being dead. I mean, you make it to sleep. So most of the times these systems, they sleep. Only there are certain blocks in the complete system which are alive. The rest are being dead, and we'll only wake them up when there is a need. Otherwise, they are not really doing anything. For example, there is a radio here, transceiver, which is sleeping. Only when the user sends a reference signal, we detect that or user is requesting for a data. There is a passive wake up receiver there, which wakes up and says, oh, this guy is asking for a data. and immediately it turns on those blocks and sends the data. So there are certain blocks in the system which are typically a reference voltage, a reference current, and a clock which continuously runs in the system. So rest all basically sleeping. They are not really active. Only when there is a need they will be active. So our objective is to understand, to get down this power. If you see, they consume microwatts of power, but we may not be having so much power all the time. So it's always running blocks. We want to basically kill them, their power, DC power, quiescent power, to very, very low value in terms of the picoamps. Now, I hope the objective is clear. So when a system, when you have a system where the battery is really a constraint, power is a constraint, you want to make sure that the blocks which always consume the power has to be kept at very, very, very low power level. Their power consumption has to be minimized because they're running all the time and they eat the battery power. So how do we design such systems is the objective of this next 2 hours to start with. Tomorrow we'll continue on this. Okay. So as a part of this whole business, we built a couple of chips. So I'm showing you here 2 circuits, a current reference and an UVLO, an under voltage lockout. I hope you can see my slides.
Yes, sir.
Yeah, thank you. Yeah. So this current reference is just 300 picoamps, the reference current, and it consumes 1.5 nanowatt of power. And with respect to temperature, the variation is 500 ppm per degree centigrade. So ppm means parts per million. So you take the quantity and divide it by 1 million, whatever you get is a number. Now, we used a voltage reference and other circuits to build this current reference. The next thing what we built was another circuit called UVLO. UVLO stands for under voltage lockout. So let me explain a couple of things here. Now you should be able to see my screen. Is it clearly visible or is there some glare on the board?
Clearly visible, sir.
Okay. Increase a little more light here. Okay. Yeah, what is this UVLO? Let me explain some bit background. Whether you take your cell phone or a computer or anything else, this circuit is going to sit on your system. So you have a battery. There's a battery here. And from the battery, you are going to run a lot of applications, right? For example, in a cell phone, you're going to have a microprocessor. There is an ARM processor. There are so many other blocks. There is a display, there is a touch screen, there is a microphone amplifier. There are so many things. Now, all these guys are connected to this battery. When the battery is fully charged, let's say that it is at 4.2 volts and it's a lithium-ion battery. And once it's fully charged, yeah. So once this battery is fully charged to 4.2 volts, you start using it. All these applications are running it. Then the battery voltage starts dropping. When the battery voltage becomes below 3 volts, you don't want to draw any more power. You want your cell phone to shut down. Now, what exactly we do is, then the battery shuts down. When the cell phone shuts down, you put a plug in a charger, and it again starts charging, and it will go to the 4.2. So there is, so how do you know when to turn on this block and turn off these blocks? So what we do is, in this application, typically what we do is, there is something called a comparator. So what this comparator does is, it's going to have a supply as a VBAT, battery voltage, and it has a reference which is generated on its own by the same battery, because this is the first circuit, this is the first comparator with built-in difference, which is going to be used by the whole system to make decisions to keep on or off. Now, whenever this battery voltage goes below certain value, let's say in this case 3, the signal output of this comparator will go low. Because if you keep turning on all other the blocks which are running on the power, on the battery, if they're still on, the battery can deeply discharge and it can damage the battery permanently. So when the battery is at lowest of its capacity, it's not advised to draw more power in order to save the battery life. And also, it can't give much current also, because it's the amount of energy available in the battery is being drained almost. So that's why we basically make sure that we look at the voltage of the battery. When it goes below certain level, we switch it off. Now, when you keep charging the battery, the signal will not go immediately. It will take some time. I mean, so for example, if the comparator output is gone low at 3 volts, then we'll make sure that it goes high at a voltage of 3.2. We deliberately had a hysteresis on it. So basically, if you observe it, when the battery voltage is falling down, at 3, it shuts down. But the signal to go high, we make sure that the voltage on the battery is more than 3.2. So there are 200 millivolts hysteresis on it. Now you may wonder what exactly happens in a modern cell phone is the moment you plug in, you can turn on and you keep doing some operations, right? So, but it shuts down immediately if you remove the power plug. That is controlled by the signal. But if you actually plug in and you keep doing it, what it actually does is, the whole system is not actually operating on the battery, but the whole system is actually operating from your power supply output. Battery is actually meanwhile charging. Once the battery voltage goes above 3.2, battery is shorted to, I mean, the system is actually running from the battery. But when the battery is discharged, when you connect a charger, it's actually running from your output socket, not really from this. Okay. So the point here is, in any system when it's running on a battery, there should be a comparator which tells what is the status of the battery. Is there enough voltage or not? If it is below certain voltage, like in this case 3 volts, shut it down. If above 3.2 volts, make sure that the system is on and it's just running as expected. Okay. Now with this background, we also, since we are going to build a system which is running on a voltage from a capacitor and from a battery, we need this circuit. So along with the reference circuit, this is also one of the circuits which is a part of the any analog and mixed signal system. Okay. Now, so going back to this slide, you can see the silicon chip, which is being taken through a microscope, this photograph. And this UV low is very, very small, few micrometer square area. This consumes a 200 picoamps of current, but in these applications, we targeted it to work from low to high trip point is 1.28. That is the time when the system turns on, and high to low trip point is 1.12 volts. Now I'll show you how do you design these circuits at such a low power. That's an objective. Okay, so the whole of this work is based on one simple circuit like this. So basically in this circuit, there are only two transistors, only two. There is transistor M1, there is a transistor M2. M1 and M2 transistors are not same variety. They're different variety, right? One, let's say, so let me explain you some little background. In a process technology, for example, you want to build simply this reference circuit. The first question you get is, who is going to fabricate this circuit, right? That's the foundry. So there are many foundries, right? For example, there is a foundry called EMC 180 nanometer, UMC, and there is a foundry called TSMC. There's a foundry called Global Foundries, like that. There are many foundries. The Texas Instrument has its own foundry. So they have different technology nodes. The technology node can be basically defined based on the channel length of the device. So if I said TSMC 180 nanometer, it's a TSMC technology. It's from Taiwan Semiconductor Manufacturing Company. So in any technology, basically you are going to have two devices, so one NMOS, one PMOS. Of course, everyone knows that. These NMOS and PMOS devices are again categorized into two categories. One devices are called core devices, other devices are called IO devices. So the core devices are generally for a 1.8 volts, 180 nanometer CMOS technology, they are 1.8 volts devices. For a 180 nanometer technology, the IO devices are going to be typically 3.3 or 5 volts based on the type of the battery you are using. So why do we have two varieties of supplies? The simple reason is that 1.8 volts are used to run a lot of digital and analog circuits. And 3.3 volts transistors are used to interface with the external world. For example, a battery. A battery can be working from 3.6 volts, for example, then you can use 3.3 volts. If the battery is working from 5 volts, you can use a 5 volts IO devices. So you are basically going to have two varieties of devices. One is core, another is IO. You are going to get only two varieties in general, without any paying extra mask cost. So these core devices for this technology is 1.8 volts, and for IO to connect with external world, you are going to use 3.3 volts devices. Now, along with these NMOS and PMOS, see, NMOS also has 1.8 volts NMOS, 3.3 volts NMOS. PMOS has 1.8 volts PMOS, 3.3 volts PMOS. Along with these two devices, as of course, why these IO devices are different from core is because core voltage we want to keep low. As you must have studied in basic digital integrated circuit design, the supply voltage is VDD, then the power consumption of the supply voltage is given as CV square F. If the supply is lower, the power consumption of the digital block is lower. That's why we want to keep the supply of a digital system lower and lower, right? That's what we do. Now, the point here is, along with these two devices, you are going to get another flavor of devices. They're called native devices. Native device, I mean, the threshold voltage of those devices is going to be 0. For all the IO devices and the core devices, in general, they are their supply voltage, their threshold voltage is between 300 to 800. If it's IO device, it's close to 700, 750. If it's a core device, it's going to be between 350 to 450, something like that. Now, but along with these two devices, you are going to get two more devices, NMOS native device of 3.3 volts and MOS native device of 1.8 volts. You get these two devices as well along with the devices you have. So these native devices have a threshold voltage 0. It means if I apply VGS of 10 millivolts, it starts taking current. But if I have an IO or core devices, they don't leak much current, right? So you can use any of these devices for free. They don't cost anything. So then what we do, we make a design, we simulate it, we make the layout, and we send it for the fabrication. Then once fabrication is done, there will be packaging. Once it comes back in the lab, we test it. That's what we do. Now, why did I explain all this story? Because to build this circuit, I need two varieties of devices. So in this example, the transistor M1 is actually a native device, and transistor M2 is actually a normal device. This device is the native device can be 1.8 volts device or 3.3 volts device. Similarly, bottom can be 1.8 or 3.3. Okay. Now, how does this circuit work? Actually act like a reference. So the characteristic of a reference is it should not change its voltage when the temperature changes. If I sweep my temperature from minus 40 degrees to 125 degrees, my reference voltage has to be constant. At the same time, even I change my supply from the lowest value of, let's say, 0.5 till 3.3 or 4, whatever is the supply, then the reference voltage should not change. So these are the two typical characteristics of any reference. It should not change with temperature. It should not change with supply. Along with the supply and temperature, there is something called process. Ideally, it shouldn't change with process. If it is changing with the process, there should be a way to trim the circuit, right? So that's why we do something called PVT analysis in any of these analog and mixed signal systems. The P stands for the process, T stands for the voltage, T stands for the temperature. The voltage there is a supply voltage, which can be 1.8, can be 3.3, can be 5, based on the device you are picking up. If you're using 1.8, of course, you can use 3.3 or 5 volts devices, but their VT is high. It may not able to conduct as much current as you expect for a given gate source drive. So that's why, in general, we use with 1.8 volts devices, core devices. Now, let's say that I have two core devices, one core device, M2, and one M1, which is also 1.8 volts device, but it's a native device. What happens is, when you fabricate it and when it comes back to the lab, all these devices are not going to behave as expected. I mean, let's take a M2 device. M2 device is 1.8 volts device, and it has, let's say, typical VTH of 400 millivolts. Now, this VTH can be minimum of 350 and maximum of 450. It can vary so much. What does it mean? Why is it varying? Because when they keep fabricating each device, every time they fabricate each chip, there is no guarantee that you get every device with the same threshold voltage. The simplest reason would be these are all made with a chemical process, right? There is an ion etching. There are so many processes. There is a diffusion. There is a metallization. In this whole process, sometimes the threshold voltage of the MOSFET comes out to be 300, sometimes 350, sometimes 350, sometimes 400, or sometimes 450. But what is guaranteed is these are the extreme numbers in lives in between this, right? So that's why it's very difficult to control these parameters of a MOSFET, like mobility of a transistor, electron, or thickness of an oxide, or a diffusion of the drain and source regions. They are quite difficult to control. Because of that reason, there is something called process variation. Because of the process variation, these MOSFETs are going to lie in some space. I mean, my threshold voltage can be anywhere between 350 to 450. My mobility of the electron can be anywhere between 500 to 700, something like that, whatever, some numbers. And thickness can be maybe 7-8 angstroms to maybe 10-12 angstroms, whatever the technology is. So it's very difficult to say what exactly is the thickness and the VTH. You can tell nominal values, but the nominal values need not be the same every chip you get, every time you get the chip. They're going to vary. Now, the fundamental reason for the variation of this is because of the process, bunch of chemicals and diffusion and ion implantation, etching. In this process, you cannot basically make sure that Every chip is going to have the same characteristics. Every device on the chip is going to have from chip to chip same characteristics. They are going to vary. So because of this reason, we are going to have a process variation. So typically the foundry maps this process variation into 4 categories. See, I'm building the whole thing to discuss the further. Okay, now what are all those? Let me just switch to my board. Okay. So there are basically the 4 corners. It's called TT. T means typical. What is here? First one stands for the NMOS, second one stands for the PMOS. Then next is called SS, FF, SF, FS. So your chip is going to stay somewhere in this space, not exactly in these corners. So typical means all the parameters are at nominal. Slow means the threshold voltage becomes higher. Mobility decreases. It's slow device. FF means threshold decreases, mobility becomes more. SF means here both NMOS and PMOS are going in the same direction. SF means NMOS threshold increases, PMOS threshold increases. NMOS threshold increases, PMOS threshold decreases. Similarly, FS means NMOS threshold decreases, PMOS threshold voltage increases. But this S is not same as this. So they are different. So what happens is, in this case, any design you do, you have to basically make sure that these are like extreme corners. So if I try to make a space, if SS is here, FF is here, PT is in the center, SF is somewhere, FS is somewhere. So in this small space, your chip can fall anywhere. It can have any VTH, any mobility, so on and so forth. So whenever we do any design, we make sure that it's inside the box, and these are like extreme cases. You have to make sure that it works in extreme cases.
Madam,
Okay.
చెప్పండి. మీరు ఒక నిమిషం.
Okay. Yeah. So do you have any questions so far, or shall we go ahead with our presentation?
Sir, sorry to disturb you, sir. Board is not clearly visible, sir. Some glaring effect is there.
Oh, is it? That's what I was asking at that time. Okay. Oh, you should tell, otherwise I know. Is it better? It's still same.
It's better, but that light. Okay.
Now it should be okay, I think. Is it okay now? Okay or no?
Still, it is not clear, sir.
Still, it's not clear.
Initially, that was clear. Initially, first time you have written that was.
No, these 2 lights are falling on it. I understand the reason. Yeah, this is the best I can do with respect to lighting is concerned. But let me do something. Okay, don't worry. I don't use it much unnecessary unless it's needed. Okay. Okay. So is it clear the concept so far? Shall I go to next topic? Next step?
Yes, sir. We are following.
Okay. 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 So now we want to build a circuit like this, which basically had two transistors. My computer is stuck a second. Okay, so basically we have two transistors. One is native device, one is this normal IO device. IO device, whatever device, doesn't matter, IO or core. We have two varieties of devices. So, can you hear me?
Yes, sir.
But my,
Yes, sir.
this guy is got stuck. So what do you see? Do you see my screen or nothing? What do you see on my screen now?
Oh, sir.
Yeah, my browser got stuck.
We are able to see only participants list, sir.
Correct. Because it is stuck. It's not moving to this. Let's wait for a few seconds. Hello, can you hear me now?
Yes, sir.
Yes, sir.
I got disconnected and just went back. Can you see my screen back? No.
Yes,
Board
sir.
is
Able to
visible.
see.
You are seeing board?
Yes, sir.
Yes, sir.
Share screen.
Now it is
Presentation
clear.
is visible, sir.
Screen is visible? Okay, thank you.
Yes.
Yeah, so this is the circuit I was talking. So this device is a normal device. This device is a native device whose VT is 0. So when I connect them like this, then what happens is the transistor M1 has a 0 VT, VT close to ground. This guy has some VT around, let's say 350, 400 millivolts. Then when I basically, because these two devices are in series, when I try to equate the current through this guy with this guy, then I can actually derive the expressions for the VREF. So what current? Because this transistor basically is connected gate to 0. If you see the transistor M1, it has a VGS of negative value. Because of that reason, the current going through the M1 is very, very small, and it is actually in subthreshold conduction. So when the device is in subthreshold conduction, the current ID is related to its VGS and VDS through an exponential relationship. If we assume that the VDS of the device is more than 100 millivolts, then you can say that actually ID doesn't depend on the VDS. You can simply say that the expression for the ID can be simply written as
Sir, 1 second, sir.
yeah.
Sir, I have shared one link, sir, bitpaper.io. There you can write using your mouse, sir. It can be opened in browser itself.
No, I don't have that stylus. That's why I have a difficulty here. Yeah. This is not clear. My board is not clearly visible still. This file numbers. Yes. Do you know how to set up the camera settings in this high resolution? Somebody can help.
Sir, give me a second, sir. I am sharing my screen. Hello, sir.
Yeah.
This is Parthsarthi.
Yeah, please tell me.
Sir, this is bitpaper. You can online you can write using your mouse, sir. Is it visible, sir?
I know, but it's very difficult to draw with mouse. If it's a stylus, it's easy. I understand what you are telling.
Okay.
I got your point, but it's very difficult to draw with this unless we have a proper stylus.
Yeah, okay, sir. Thanks.
Okay, anyway, I hope you can see something already big letters otherwise. So basically the equation ID for a MOSFET is given by some reverse saturation current times W by L, E power VGS minus VTH of the device divided by KT by Q. So this is an equation of a MOSFET when it is in a deep subthreshold region. So we can use this equation and derive the reference voltage. So if we go back to our presentation, so our presentation shows that there are two devices, M1 and M2, both their currents are equal. Since it's going to become independent of VDS, so M1 transistor you have to replace with a minus VREF. M2 transistor you have to replace that with plus V reference, and both transistors are carrying the same current. When you equate them, you get a reference voltage. You can solve for the reference voltage because there is only one unknown and one equation. We can solve it and we get an expression something like this. So what this equation shows is that this VREF is basically the difference between threshold of these two transistors. For example, the threshold of the one is very, very low. Actually, it need not that these two devices have to be different. It need not be a native device. In this case, it happens to be a native device. So I can take the difference between these two VTH2 minus VTH1 plus VT here is KT by Q log alpha divided by some M1, M2 or the two substitutional factors. So what is alpha? It's basically a device dimensions, which depends upon the device type. So what we can see from this expression is there is a difference between threshold voltages plus a KT by Q. Now, what is the difference between threshold voltage? Actually, threshold voltage in general falls with temperature. As the temperature increases, the threshold voltage decreases with temperature. When I take the difference between these two devices, the threshold also falls with respect to temperature. So when this one guy is falling with temperature and KT by Q log alpha is increasing with temperature. Now, if I can add them up with the right proportionality constants, I can make this voltage constant. Now here, how do I play? See, for example, VTH2 minus VTH1 slope is not in our control. It is fixed. So what we can do is VTH2 minus VTH1 slope, since it's not in our control, it becomes basically something which is falling with temperature. But VT log alpha, where VT is KT by Q, is in our control. We can play with the alpha. Alpha is the ratio of these dimensions, these device dimensions. Now, I can choose any value of width and length, and I can match the slope of this first term to the second term. Then when I match this first term with the second term, I can make this reference constant. So that's what it is being. It's being done in one of the reference works, which is given 1. Now, with this method, using just 2 transistors, you can get a reference voltage, and that reference voltage does not change with temperature. And it also doesn't change with the supply, because if you see here, this device is actually a diode connected device. This guy, if you see, it's actually looking up, it looks like a very high resistance. That's why the supply variation doesn't come. Even the supply changes, it drop across M1, and VREF is not going to change really. So because of that reason, we can say that the VREF is constant with respect to supply and temperature. With respect to process, these things vary because VTH2, VTH1 vary with respect to process. To trim this, we need to add extra devices. And you come in there, you get it in the lab and you see how bad the VTH2 and VTH1, and you trim it and get the reference voltage always constant. So what we learned from this circuit is that the reference voltage is really constant with respect to temperature and the voltage. Now, how do we use it? Because this reference voltage, what you get is some random value based on, it's very difficult to control its value. It can basically, to make it temperature independent, you keep changing these device dimensions. You made the temperature independent. Sometimes you get 280 millivolts, sometimes you get 350, sometimes you get 400. So how do we make sure that whatever voltage we want, we can get? So that's what is being explored by us. Now, whatever concept we explained here can be extended for PMOSs also. So in this case, we have a PMOS here, another PMOS here. This top PMOS is a device which is, let's say, 1.8 volts device. This is a 3.3 volts device. What we have done here is, instead of making that connection, we made the gate and source tied to each other in this PMOS. Because gate and source is tied, it just carries a leakage current. When the leakage current is going through this MOSFET and its gate drain connected, the equation, again, we can equate the current through these two MOSFETs, and we can actually, here VT1, VT0 are actually threshold voltages, and phi t is KT by Q. Now you can again see that the reference voltage is difference between two threshold voltages which falls with temperature plus KT by Q logarithm of something, where K0 and K1 depends on the dimensions of the device. So what we can say is that we can again match the temperature coefficient of the first two terms, VT1 minus VT0 is falling with respect to temperature. We can make that other one KT by Q log something raising with temperature. When we add them up, the reference voltage can be made constant. But how does this circuit useful? You can see that this circuit can be extended to get n times the VREF. Because if I simply put all of them in series, VREF, I can generate any voltage which is a multiple of that VREF. That is 280, 480, 280 into 2, 280 into 3, 280 into 4. I can generate higher reference voltage with the help of that circuit. But that is quite challenging in this circuit. Okay, now we got a reference voltage in this method, but how do we generate a reference current? The way to generate a reference current is you can basically take one device and another device. And as we were telling here, you can see from this expression, it need not that always I want a reference voltage to be a constant. I can also generate a voltage which is raising with respect to temperature, falling with respect to temperature, anything I want. I can generate something called PTAT or CTAT. PTAT means proportional to absolute temperature. CTAT means it's actually inversely proportional to absolute temperature. So we can generate anything we want. Now in this case, we can generate a voltage which can be either CTAT or PTAT by playing with the dimensions of NP0 and NP1. Now, okay. Yeah, I can generate a voltage which is proportional or it's decreasing with temperature, whatever you want. Now, I can take this device and put a lot of diode connected devices here. They're all like acts like resistors. And now I can divide this voltage into small portion, whatever voltage I want. Now now we can design another op amp and put it in a negative feedback like this. Then what happens is, when this op amp is in negative feedback, the voltage across the reference is actually Vcomp. Vcomp is fraction of Vref. Now what happens in a typical CMOS technology, the resistance either decreases with temperature or increases with temperature based on the type of the resistor you pick. Let's say that my temperature, with respect to temperature, my resistance is increasing. Then I can generate a voltage which is also increasing with respect to temperature. Then when I take the ratio of this voltage to this resistance, then I can get a current. So because of the negative feedback, the voltage across the resistor becomes the Vcomp. And that Vcomp can be made, temperature profile can be made same as the temperature profile of the R by varying the dimensions of NP0 and NP1. That way we can generate a reference current. That current can be mirrored to generate many reference currents. Many places we can copy that current. So how do we build this op amp? There's a challenge here. Now to build the op amp, again, we need a reference current, right? So what we do is we take a simple standard two-stage amplifier. Instead of putting a current source, we take a device and tie the gate to source. So VSG of both devices are 0 and both are leaking the currents. Now this circuit is really slow because it's working on a leakage current, but it works because we don't want this reference current. Once it comes up, once it's powered on, that's it. We're all good to go. So that way we can use this circuit to generate a reference current. So the two key points here is, why did we down convert this VN1 by N times? The reason is simple. If this voltage is 300 millivolts, I want to generate 1 nanoamp of current. I need a huge resistance of the order of hundreds of mega ohm. So having a resistance of very large value on chip is actually expensive. It takes a lot of area. That's why we divided this voltage and dropped across a resistor and we generate a reference current. I hope this is clear. Now, how do you measure? So we can design a lot of circuits, but how do we measure these currents? So if you have any doubts so far, we can discuss. Hello? Am I audible?
Yes, sir. Please go ahead, sir.
Yeah, if some people have doubt, we can stop and just discuss if you have some queries. Otherwise, I can go ahead. Any audience have any questions or comments so far what we discussed? How we generate a reference voltage and reference current? See, in general, in a design, right, you take a MOSFET, apply some VGS. So if you see most of these designs, the VGS is 0. We are basically turning off the device and using the leakage current to build some circuits. That's the key point here. No comments? So many audience are there.
Hello, sir.
Yeah.
Sir, is the leakage current is enough to drive the op amp?
Which one? Which one? Srinivas, can you please be louder?
Is that leakage current is enough to drive the op amp?
Yeah. That's enough. See, actually, what is drive means by you, by me, you by you is, you see here, these two devices are high thick oxide devices. This is a thin oxide device. So it's not zero current, it's a current, but it's very, very small current. So in any design, if you burn more power, you get a higher speed. If you burn very, very, very low power, the speed keeps on going down, down, down. So the two challenges in such designs are, one is the speed, which is very low. Other challenge is, the other challenge we generally get typically is the offset and flicker noise. If you can make sure by making the device dimensions large enough, which makes system further slow, yes, you can deal with such low currents.
Thank you.
So for example, the current in this branch is typically maybe 50 to 100 picoamps. In this branch, another 50 to 100 picoamps. But the driving transistor here, which can give any amount of current based on the arc. So this acts like a buffer. This MN5 acts like a buffer.
Oh.
Yeah. Any further questions?
No, sir. Thank you.
Yeah. Any others? Okay. Let's go further ahead. Now, how do we measure? Basically, we'll get a challenge. In general, we make such low power circuits, but how do we measure those currents in the laboratory? That's a challenge. So the setup we used is this. So this is a design under test. And we use a huge resistor of 100 mega ohm to 1 giga ohm. And we connect a voltage source and a low leakage 100 nanofarad capacitor. And there is something called picometer, which is from Keithley. There is a company called Keithley, which gives the picometer. But even that guy is showing, how are you confident that it's showing correctly? You want to verify it once again yourself, whether it's doing correctly. So what we do in such systems is we use a resistor, and there are op amps from analog devices which leak a very, very small input current. Now what this op amp does is, whatever is the V-sense voltage, it gives it in the multimeter. You can connect it to multimeter. If you connect directly this to multimeter, it will collapse because this is hundreds of mega ohm, and the multimeter input impedance will be typically of the order of tens of mega ohm. So you can't really measure. You try to measure is you collapse this node. That's why what we do is we take an op amp and put it in negative feedback, and the output of this op amp is exactly equal to V-sense. Now this V-sense, and we have a resistor here. Now the DC current taken by this can only come from the input. Now any transient currents are needed, that will be provided with a supply cap. That cap is only to give the transient current. And the DC current, because the DC current to the cap is zero, actually the total current, for example, there is a transient in this design under test. The voltage immediately dips. When the voltage dips and the voltage falls down, then the current will be, the sudden transient current will be given by the cap, and the cap will slowly get charged through this huge resistance. Now, larger the cap, smaller the ripple. So that's what we do. So now all the ripple current is supplied by the cap, and all the DC current will come from the actually all the current needed for the system will come from the input. So on an average, if you see this voltage, this Vs minus V sense by R, if you do Vs minus V sense by R, that gives you an average current. That is the current which you can measure. How are we measuring? Because V sense we can see, look at in the multimeter and tell. So that's how we can measure the very, very low current, and which you can further verify back using this picometer. If these two are showing the same reading, yes, you're understanding correct. So two things here critical is you have to make sure the cap leaks very small current, and you pick an op amp which is having a less very, very small leakage current at the input. So these are the current consumption of this reference what we discussed. As we were talking, there will be three different there are 4 or 5 different types of corners: slow, slow, fast, 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 slow, typical, like that. But we Typically, we have used the same variety of device, so it makes sense to use slow, fast, typical. You can see as a function of the temperature, the currents vary, and especially in slow and typical cases, the current is below 2 nanoamps, much below 1 nanoamps at room temperature. So that is the point. And this is the current which is measured in the laboratory. As we increase the temperature, the current reference is around 300 picoamps. You can see more or less it's constant. So this is some of the comparison with the existing literature. You can see that. So this work has a current of the reference current of 300 picoamps, which is measured in the laboratory, but in the simulation, which is being designed for 275 picoamps, and the temperature range is -10 to 80, and it occupies an area of 164,000 microns square, and the technology used is 0.18. So basically, we can design the circuits which go for such low power. Now let's design that. Let's understand another circuit. The next circuit, what we want to see is the under voltage lockout circuit. How does this work? So to appreciate this circuit, we have discussed before that there is a device which is a low VT, and I have two devices which are diode connected like this. You see here VGS is 0 for this device. For these devices, gate and drain are connected. They are diode connected transistors. And this transistor MP0 is a leaking current into these two devices, MP1 and MP2. Now, because these two are leaking the current, this MP0 is leaking current, you get some voltage. As we have discussed before, we can actually change the dimensions of MP0 and MP1 such that the reference voltage becomes constant. Now, if I put three devices like this in series, I can get 3 times VREF. Note, these two devices are not same. One is a low VT, another is a high VT device. Now, as we discussed further before, we can take a device and put them in series like this, many devices. Then each device here is going to split. Voltage across each device is this VREF by N. Across MPDN, for example, if you take the voltage across is VREF by 1, N. MPD1 is also VREF by N. So why are we doing it? So we want to generate a voltage which is VREF plus some K times VREF by N. So I hope that is clear. Let's try to see what exactly happens. Let's say that I sweep my VDD from low to high. Then what happens? So these two are high voltage devices, high threshold voltage devices. Because of that, when I'm increasing VDD, my VN1 and VN2 basically tracks as VDD increasing initially. After that, my VN1, VN2 will become VREF. It becomes constant. Even if you change the VDD, it doesn't change. It tracks, it follows the VDD and it becomes a VREF. And similarly, VN1, it tracks the VREF, 2 VREF, until 2 VREF of the VDD it tracks, and after that, again, it flats. It becomes flat. Because after that, how much ever VDD increase, they will stay just at that VREF. So VN1 is at VREF, 2 VREF, VN2 is at VREF. You can see that from this plot. Okay. Now, what is this? Now, you see here, there are many switches, S0 to Sn. I can connect my VN3 to any of these nodes by turning on the switch. For example, if I connect S0, the VN3 becomes VREF. If I turn on S1 and open all the other switches, my VN3 becomes VREF plus 1 voltage across 2 devices voltage I get. So what is VN3 now? VN3, see, if I have VREF and I put N devices like this, each device is going to have a voltage which is VREF by N. Okay. Now the voltage across this is VREF by N, VREF by N, VREF by N. If I tap from the bottom, it is Vref. If I turn on the S1, my VN3 is going to be Vref plus Vref by N. If I tap through S2, I'm going to get Vref plus Vref by N into 2, because 2 devices are coming in series, their voltage will come. Like that, if I have a K there, I can get Vref plus K times Vref by N, because this total Vref is divided equal into all these guys. Okay, that's why we have written that VN3 is actually Vref plus K times Vref by N. Okay, now how do I do that? Now, how do I use it? So as you know that, as we discussed in the starting of this session, that to design an under voltage lockout circuit, which is actually a comparator sitting on the power supply, we wanted to make sure that we get enough hysteresis. Hysteresis means what? When I'm changing my supply from low to high, the output goes from low to high at one point and high to low at some other point. So these 2 points are not same. In general, if you have a comparator, if the reference voltage is 1 volt, if I'm increasing my input voltage, when input goes more than the 1 volt, it basically becomes low to high, high to low. And similarly, when I'm reducing the supply voltage, when it becomes below 1 volt, again, it switches its direction. But if a comparator has a hysteresis, what it does, when the supply is going from low to high, it trips at let's say at 1 volt. But while coming from high to low, it may not trip at 1. It may be at 0.8, at 1.2, based on the application, you can set it. So why we have broken this? Because we want to make sure that we create a hysteresis with this comparator. Okay. So what we understood so far is only the portion which we have in the left side, right? So here, I'll repeat. We are having a MP0, which is a low VT, and we have two references. Two reference voltages we are getting, which are VN1 and VN2. VN2 is Vref, VN1 is 2 Vref, because two same devices are there. Now, this device MP1 across that, we put bunch of diode connect transistor. The total voltage across this will be divided into many small voltages. Now, we are using a lot of switches and generating a VN3. By choosing the right value of switch, we can generate VN3, which is Vref plus Vref by N times K. If K is 0, you get Vref. If K is 1, you get Vref plus Vref by N. If K is 2, you get Vref plus Vref by N times 2. 2 times Vref by N plus Vref you get. So now what we are going to do is, you keep this parking. What is this transistor? If you observe MP1B, MP0B is actually the comparator. The whole left side is actually a reference generation. So how do we generate a comparator using just two transistors? That can be seen here. You know that this device is same as MP0. MP0B is same as MP0. Okay. Now, this guy is leaking a very small current. Now, what happens is, this VN3, let's say that VN3 is shorted to VN1. When VDD is increasing, VN3 actually follows VDD until it becomes 2 Vref, because VN3 is now shorted to VN1. So VN3 follows till Vref, 2 Vref, and after that VN3 becomes short. Now, let's keep this aside. Now let's say that I'm trying to sweep VN3 from 0 to a certain value. Then what happens is, if you observe, the bottom device is a low VT device, the top device is a high VT device. When I'm increasing my voltage at the gate from low to high value, this transistor, to start with, VN3 is actually following VDD, let's say. This VN3 and VDD are increasing together. Then what happens is that the current through this guy is very small. But if I make my VN3 sit at 0 and I increase the VDD, then initially the Vx will be 0 and Vx will start tracking the VDD. Now, what happens is, if I make VN3 constant and VDD I keep increasing, the transistor MP1B is getting a lot of gate to source voltage, or source to gate voltage. Then the Vx will actually becomes equal to VDD and tracks. But the point here is that if my VN3 is equal to VDD, then the Vx will sit at 0. The reason is the top transistor has a higher threshold voltage compared to the bottom transistor. If both VSGs are 0, then the bottom guy is asking for the more current, the top guy cannot give the current, so Vx crashes down to 0. Now, if I fix my VN3 and keep on increasing the VDD, there will be a point at which the transistor MP1 works like a shot and Vx will track the VDD. That point is exactly the point at which the difference between VN3 and VDD becomes equal to Vref. So by adding a device which is MP1B is exactly like MP1, MP0B is actually like MP0. By doing this operation, the Vx node initially will be 0 and it jumps to VDD and tracks the VDD when the difference between VDD and VN3 becomes a Vref. Okay, so with this understanding, what we can do is we can see these waveforms. When I keep on increasing the VDD, now I can choose any switches here. Let's say that initially I turn on a switch called K. K can be arbitrary number. When I do this, when I'm increasing the voltage, my VN3 becomes Vref plus Vref by N times K. Now, that is the voltage which is available at VN3. Now, whenever VDD goes more than the VN3 plus Vref, then it actually trips from low to high value. That you can see here. So whenever the VDD is increasing at Vref plus Vref plus V plus Vref by N times K, that is 2 Vref plus K Vref by N, the comparator basically goes, this output goes from low to high. Why is that happening? VN3 is fixed at a Vref plus Vref by K times N. Now, that Vx will become at certain voltage higher. Until then, it will be 0. At what voltage? When the difference between this becomes Vref. That's why it is becoming 2 Vref plus K times Vref by N. Once the output of this changes, immediately I change my switch position to one switch. For example, if I'm at S2, I'll turn on S1. Now the comparator reference has changed to a lower value. Because it changed to a lower value, I can change anything. I can change 2 switches, 3 switches, whatever. If I reduce my reference to the comparator VN3 by turning on, if I am at S2, if I make S0, it becomes K minus 2. So I can do K minus 3, K minus 4, whatever I want based on the number of switches I have, number of amount of division I have. So what we are telling here is that when the VDD is going from low to high, I trip at 2 Vref plus K Vref by N. But the moment I tripped, I changed which switch to be turned on. I jumped 2 switches down. That's why I get V2 Vref plus K minus 2 Vref by N is a reference as VN3 now. When the VDD falls, Vref plus K minus 2 times Vref by N plus a Vref, it again trips. That's why we get 2 Vref plus K minus 2 times Vref by N. So this is low to high trip point. This is high to low trip point. Now, this is the power consumption of this circuit. You can see that at room temperature across all the corners, it is much below a nanoamp. And these are measured low to high and high to low trip points. You can see that they're almost constant with respect to temperature, and there's a hysteresis. If this is clear, then we will try to use these concepts to build a voltage regulator. Any doubts you have? So far, so good. There's any break or it's continuous session? Hello?
It is clear, sir.
Yeah. But do you give a break of few minutes or you continuously go up to 2 hours? What is your plan?
The schedule given to us, it is in between 2 to 4, sir.
Okay. So if you want, you can take 5 minutes break. Don't log out. So right now the time is 3:30 in my watch. 3:35, I'll restart again. You want to go to washroom or drink water, you can just do it. 3:35 will start. My watch is 15 minutes faster. So 3:30, we'll meet at 3:35. Okay? So don't log out. I'm just here.
Okay, sir.
Hmm. Okay, let us start. Can you hear me?
Yes,
Yes, sir.
Any doubts you have? Any doubts or comments so far? No, oh my God. Okay. Okay, if all good, we'll go to the next topic. Yeah, so far we build these circuits. Now let's try to build a regulator, a voltage regulator, which can give any amount of load current it needs, from very low current to the very high current. Yet it consumes very, very low current, low quiescent current. Now you can see from this that so this is one of the regulator what we built. So these two, this is also based on the same concept. You can see that there are two devices here, one native MOS device, one IO MOS device. This native MOS device, the gate is grounded, which we discussed before. And we said that you can basically size them to get a reference voltage, whatever you want. We also discussed that this can be built using a PMOS and a PMOS. Actually, it cannot be a PMOS. It can be a PMOS and MOS combination. So this is a regular MOS which has a low VT, and this is an IO MOS which has high VT. I can put them like this and size them. Still, I can get a reference voltage, whatever I want. You can see that VT2 minus VT1 plus KT by 2 times log alpha. I can play with the alpha, which is the dimension of the device. I can make a reference voltage constant. So basically, from modified TT reference, I can get a constant reference voltage. Now, how am I going to build a regulator? Actually, we're adding one extra device. I can make a regulator out of it. How? Let's say I take a native MOS device. Now, when I put it back in this way, in a feedback through a beta, let's say I have a regular MOS, I have a IO MOS, I have a native MOS, and my V out I take through a beta and feed back to my gate. Okay. Now there are two devices here, M1, M2. Both the currents are equal because they are in series. Now what happens is the current of this I1 cannot go to the gate of M3 because it's a MOSFET. Gate cannot take current. So I1 has to be equal to I2. Now what happens is if I keep on changing my voltage, my load current here, let's make beta equal to 1 now to start with. Now, as we discussed, if my M1, if my I1 and I2 are equal, then the V out has to be equal to Vref, irrespective of the load current I take. If I'm drawing a load current, suddenly I draw a load current, if V out drops, then what happens? If the V out drops, the I1 will charge this node up and brings it to some value. Finally, in the steady state, my I1 has to be equal to I2. If an I1 and I2 are equal, then this voltage has to be Vref. There was no another choice for it. So it means this M3 is actually helping it to drive the load. But at the same time, by closing in this way, I always make sure that my V out is equal to Vref. But if I add a beta here, this is Vref, this will become V out is equal to Vref times beta. It means Vref equal to beta V out by beta. Or if I can say that my Vref is equal to beta times V out. I'm sorry, Vref is equal to beta times V out. It means V out equal to Vref by beta. If the beta is less than 1, I can generate any V out. But the point here is that by putting it in a closed loop like this, I can give any amount of current. But for example, if I put a load here on this Vref, the voltage itself will crash down because the current which is given by M1 is taken by the load. But here the current is provided by the M3 because the current is provided by the M3 because there is a feedback. The feedback will make sure that always the load current is given by the M3. And since I1 and I2 are equal, the voltage from the gate to source of M2 will become simply Vref. I hope this is clear. Now, what is the advantage of this? It doesn't depend on the load current. You can drive any load you want. So, for example, let's see some of the. Okay. Now, the disadvantage of this circuit is when the load current suddenly jumps high or low, the voltage will dip or the voltage will go high. It takes a long time to settle because, see, for example, if this node voltage, I increase the load current, then what happens? The load current is actually given by M3. Now, the gate of M3 is settled at some value. When I suddenly increase the voltage and when the load current, the voltage drops. Now, how will the voltage on this output will raise? Only when the gate voltage of M3 will raise. Gate voltage to raise, the I1 has to first initially charge the gate. In the steady state, I1 will become I2 and the Vout will go again back to Vref. But the current of the M1 is very, very small, hundreds of picoamps. Because the current is so small, it takes a long time for the gate of M3 to be pulled up. Hence, the Vout will take a long time to settle. To fix this problem, what we have done is, we have two detectors, G1 and G2. The G1 and G2 are exactly replicas of G0. So we took the Vout, we generated here the Vref. Vref is here. 5% above the Vref, 5% below the Vref, we took two voltages. And we are giving it to the same network which is as G0. G1, G2 are the same network. Now what happens is, in general, G0, in general, what is the output of the this G2? Because it will be high. The reason is, it will be, if I have a Vref, I'm taking a value lower than the Vref. That means the M11 actually is getting a lesser drive than it can. So the output of this M11, the drain of the M11 will sit at VDD. But if my output dips, then this guy also dips. When this dips, sorry. When I have a load step, this guy rises up. When it rises up, this voltage will change. The change in this voltage basically wants it to. So there are two cases here. One is sudden increase in the load, sudden decrease in the load. Let's try to take as case one. Case one is increase in the load. If the load increases, right, then the Vout will drop. If Vout drops, then what happens? That M3 gate has to go high. M3 gate can go only high by supply. M1 only can supply that current, but the current is very small because the gate source is tight. Now what we are doing here is, we are taking 5% more than the Vref. Whenever it drops, this also will drop. So in general, what we are doing, we have a Vref here, we have 1.05 times Vref here, but G1 is same as G0. Because of that reason, the output of this guy is to sit with is actually low. Because this is low, M9 is on, M7 is actually off. There is no current in M7, right? If there is no current in M7, there is no current in M8, because the gate of the M7 and M8 are pulled to Vin through M9. Because of that reason, these two transistors are off, and this network is M8 is in general off. But whenever the output dips, right, immediately M4, M5 out drain goes high. When it goes high, this transistor is off. When this transistor off, there is a current. That current will be mirrored in M8, and it will pull this node very fast up. But similarly, we cannot do anything about, let's say I suddenly drop the load current. If the load current drops, the Vout will go high. When the Vout goes high, the feedback network will make sure that the gate of M2 will go high. That will pull and discharge the CC. Because now the current can be discharged by the M2 very fast. We don't need any extra network. So adding these two, G1 and G2, helps to make transient faster. Now you can see that G0 consumes 187 picoamps, G1 consumes 200 picoamps, G2 consumes 195 picoamps. These are all the currents which are measured in the lab. And this beta network is made using the resistors. That's why it's consuming 11.6 nanoamps, unfortunately. And the total current is 12.2 amps. Now, these are the sum of the results what we measured in the lab. You see that with increase in the temperature for a Vin of 1 volt, the Vout is almost at 800 millivolts because we targeted 800 millivolts. Now you can see in this plot, the temperature is increasing for different load currents. Sorry. In the first graph, Vin is fixed and the load current is increasing. You can see that the output is almost at 800. In the second graph, temperature is changing and the load current is fixed, and different Vins all the way from 1 to 1.8 volts we sweep. Sorry, 0.85 to 1.8 volts we sweep. the output voltage is more or less constant. Now, this is the graph where we are sweeping the load current at a given temperature at different VNs. You can see that the output voltage is almost constant. If I have a sufficiently large VN, it can give up to 1 to 10 milliamps also it can give. Now, this is the power consumption of the total system. As the temperature increases, the supply current changes. If we see, without beta network, the current is actually at low temperatures, much below 100 picoamps. As temperature increases, the current goes. It can, at 120 degrees, it can become at most 10 nanoamps, not more than that. So this is what it is. And there is something called power supply rejection ratio, power supply rejection for any DC, any regulator. Now we can see that as the frequency increases, the PSR initially is low, but later it becomes bad. The reason for it is we can actually know that there are two nodes in the system, in this regulator. One pole is here, another pole is here. So two things are the worry here. One is the stability, another is the PSR. Stability wise, this regulator works really, really good because there are only two poles. It becomes never unstable. The phase margin can become bad, but it will never become unstable. But PSR wise, as long as the loop is active, I mean at low frequencies, the loop is active and the output can reject the variations in the supply. But as the frequency is increasing, the loop becomes like an open loop and there is no gain in the loop. Because there is no gain in the loop, for any change in V will couple to the output to this gate of the M3 and couple back to the V out. Like that, we get a very bad PSR. Okay. Now, this is a complete schematic of the proposed regulator. These are the results. And we have actually derived what are the poles and zeros, and we actually measured it in the lab. You can see that a lower gate cap at M3, we can get a better PSR to up to hundreds of H, but with a larger size, it becomes bad. You see here, it goes still up to -5. So this is a load transient, as I was telling you. So this is an output voltage 0.8 volts. Suddenly I did a load step here from very low current to 1.2 milliamps. From I think 350 microamps to 1.2 milliamps, we did a load step. Then as you see that the output dropped and it took a long time to recover without that extra transient improvement circuit. When we added a transient improvement circuit, within 25 microseconds, it recovered. So this is for load step for different supply voltages. You can see that everything got recovered within 20-25 microseconds. Smaller the load step, smaller will be the dip in the voltage. So this is the complete chip photograph. You can see that the G0, G1, G2 are here. They are the main core of the amplifier regulator. They're very, very small. And there is a huge feedback loop. Even after using such a big resistor, we have a power consumption of 10 nanoamps. Still, it is so big. And this M3 is the output load, driving transistor. It's a photograph of the chip, which is taken on the microscope. So this is the story. If you have any doubts, we can discuss on this subject. Hello? Any doubts? You can chat also, you can click here if you want. Am I audible?
Sir,
Yes, sir.
Yeah. Any comments, any questions? Shall we go ahead? If we have no comments, questions, then we will go to the next topic.
Yes, sir. Go ahead, sir.
Okay, thank you. Okay, so the last topic as a part of this discussion is how do we use this circuit? So we used all these circuit concepts to build one of the systems. Yeah. So this is one of the circuit system what we built using all these concepts. So it basically can harvest energy from three powers: solar, RF, and piezo. And you can see the chip microphotograph with showing all the different blocks of the system. Rectifier, there's a regulator, there's an oscillator, there is a comparator, there are switches, there is a V-store OK comparator, sampler, references, startup, and so on and so forth. So I think I'll quickly explain what is this. It's basically a buck boost converter working at very, very low power. The typical power consumption of the complete system is 8 nanoamps. Now, how does it work is in any buck boost converter, you energize and dump. S0 and S2 you use to energize, S1, S3 you use to dump. So there are two innovations or important things what we added to the system. The first thing is in all these transducers, you want to regulate the input. Now to regulate the input at certain value, why do we do that? Because in any energy harvesting, the transducer is modeled as a power source. Power source means a voltage source in series with a resistance, let's say. Then voltage source in series with a resistance basically has, you can't get maximum power out of it by shorting it or opening it. To get a maximum power, the load resistance has to be equal to source resistance. Other way to look at it is that I have to make sure that my voltage at the terminals of that source is actually off of the open circuit voltage. That means I have matched it. And all these transducers, we make sure that their voltage is regulated certain value. Now, if you see here, what we do is we basically look at the voltage on this VB. If it is below or much above the off of the open circuit voltage, we try to change S0, S2 frequency. So if, for example, you can see here, there's a comparator. If this voltage VB is more than half of the open circuit voltage, we turn on the inductor and take a packet of energy, then this voltage will collapse. Then we dump that packet to the output. Whenever the VB goes below that, we stop it and it again charges back to that value. So we can use the comparator to do this operation to regulate the input voltage of the VREF. But in general, these circuits like comparators consume a lot of power in these applications because they have to be fast enough to make sure you don't collapse the VB2 down to 0. If you turn on S0 and S2 and if a comparator is slow, by the time you realize VB will become 0. That not to happen, that is to be avoided. If you want to avoid that, then we have to make sure that we make a comparator fast enough. To make the comparator fast enough, we need to burn a lot of power. So that's why what we have done is, actually in this whole business, once input power is fixed, VB is going to regulate a certain value. And the frequency of the output of the comparator is going to be fixed if the input power is fixed. So what we have done is we have used multiple oscillators. Each oscillator can be made very, very low power, which we didn't discuss as a part of this discussion, but we can make an oscillator even with 500 picoamps or 1 nanoamp current. So, but we can change the oscillator frequency to match with the comparator frequency. What we do is initially we start our journey with comparator. Once it reaches a steady state, We look at the frequency of the comparator and we make sure that the frequency of the comparator, oscillator frequency actually matches with the comparator frequency. Once they become equal, we turn off the comparator. We simply use oscillator to turn on and off. And we do this operation once in a while, because if the input power changes, again, we have to do this operation, so on and so forth. So for each of the transducer, we need one oscillator, because once in a while you use a comparator, tune the oscillator frequency and do energize and dump. This is what we do. Now in this process, you can see that O1, O2, O3 are the 3 oscillator outputs, and we have only one comparator that basically used to tune each of the oscillator frequency. Now, what is this guy? Basically, there are 2 concepts called in these converters. How much time do you want to energize the inductor, and how do you dump the energy in the inductor to the output? We also made them without using any comparators. So one way the people do is they take an inductor, they put a resistor in series with the inductor, they sense the current. Whenever the current goes more than certain value, they turn off. And similarly, whenever the current becomes 0, basically whenever it goes more than certain value, they turn off S0, S2, and they turn on S1, S3. Whenever the current in the inductor becomes close to 0, they turn off S1, S3. So basically they need 2 comparators, but we did this in an open loop using 2 monoshots. These monoshot times are generated such that for a given inductor peak current, it generates that pulse. For dump monoshot also done the same way. And these are details, that's not part of discussion. How we exactly do that is given here, but you can go through these slides. I can share this with you. But the point here is we can generate the 2 pulses such that you can keep S0 and S2 on, such that the peak in the inductor current, whenever it hits that value, turn off S0, S2 by looking at the VB. And similarly, you can turn on S1, S3 and keep them on till the inductor current becomes 0. After that, you turn them off. That can also be done by using another monoshot. Okay. So this is what is given here. But the point here is, how do we tune that oscillator frequency to match with the comparator frequency? That's given here. You can see that there is an oscillator which is really consuming a low power. The bias current is generated with the help of the reference current, what we learned. Now, initially, the oscillator, the COS, is actually a bank of capacitors. C02, C02, and C0. There are a lot of capacitors there. And which capacitance we are going to use is control through switches. Now we have a 6 I bias and a device and bunch of these inverters. What is our target? Our target is to make sure the oscillator frequency becomes equal to the comparator frequency. How do we do that? We do that by changing the capacitor bank capacitance. So in general, this search switch is closed. When the search switch is closed, the oscillator is in the closed loop. And when the oscillator is in closed loop, the oscillator is running at some frequency. The frequency is actually depends upon the value of the capacitor. If the capacitance is large, then the frequency is going to be small. If the capacitance is small, the frequency is going to be large, because this is basically a relaxation oscillator. So you once in this is in closed loop in a positive feedback, because 1, 2, 3, 4 inverters are there. After that, of course, it doesn't matter whether a system is in closed loop, in a negative feedback, positive feedback. What you have to make sure is that there is enough delay in the loop to oscillate. So the way it works is, when you are doing a search, you open the switch. Now, every time the comparator output goes high, you charge the C oscillator to VDD. And again, when you charge it to VDD, V oscillator also goes to VD. So this is at VD, this is at VD. Now, you keep discharging this oscillator, this capacitor with an I bias current. I bias is fixed. Now you keep on discharging. When this near voltage becomes below the threshold voltage of this inverter, the output will go low. So what we do is, we initially charge it C oscillator to VD, and the V oscillator is also at VDD. The capacitor is slowly discharging. Now, the comparator output went from low to high. Then we did this operation. We charged the C oscillator to VD. And again, we are waiting. Next, when the comparator output goes again high, this is the frequency, right? It went high here, and the next edge comes. Between that time, that is the frequency which it defines. So we basically charge this capacitor to VD, and we are discharging it. And whenever, for example, let's say that my comparator output went too high. By the time my oscillator, this VOS is still VD, it means I have a wrong capacitor. I have a more capacitor than needed. What will I do? I keep decreasing the capacity. Then if my capacity is too low, this should have gone low by the time the next edge of the comparator output goes high. So we basically tune to the right value of the comparator frequency, as oscillator frequency, by changing the C oscillator until the oscillator frequency becomes comparator frequency. That is done through this flowchart. So now how do you do it very fast? We can use a successive approximation algorithm, and we can actually get to the steady state value very fast. So this is the efficiency of this system, which is calculated versus simulated to see how well it's modeled. And as a complete overall architecture of the system, you can see that from 3 transistors we are harvesting, and this is an inductor we are energizing and dumping. There are 3 oscillators, 1 comparator, and bunch of switches. There is a startup. There is also in this startup, there is a UVLO, there is a lot of other blocks. There is a digital controller. There is also an LDO to give the output. There is also half an hour clock to basically read the sensor measurements. So this is a startup system. And I think it's all not very much needed for you, but I can quickly explain. In an energy harvesting system, the battery is completely drained. Then you should have a way to bring up your system, because all the circuits in a design needs at least 1 volt to reliably operate. How do you design it? So the typical way to design it is to design an oscillator which can oscillate from 200 millivolts. That is possible by using a low VT and medium VT devices. Then use a charge pump to generate a higher voltage. Use that clock, boosted clock, to energize and dump and bring up the system. Once the system is at a certain level, then you can actually turn on the main converter and do the energize and dump. So this is a schematic of the power switches, because these big switches S0, S1, S2, S3, to turn on then off them, we need a high voltage so that their on resistance will be small. So this is basically a charge pump. You can see that the VD charges this 75 picofarad cap like this. Whenever the energizer dump pulse comes, this node voltage go high VD. So already capacitor is charged to VD, so it generates a 0 to 2 VD. And use the signals which you are getting from energize and dump, and you can drive the switches between 0 to 2 VD. So there's a simulated power losses and power consumption. You can see that all the blocks, when they're on, right, comparators, references, you see the references are consuming 4 nanowatts of power. Right, actually the current is much below a nanoamp. The supply is more than 1.5. That's why we are, what supply we're simulating? Yeah, it's around it's at very, very low supply voltage, very high supply voltage, around 1.5. Actually, the power consumption of these blocks of the references, what we learned are all is below 4 nanowatts. You can see that most of the power consumption of the blocks are all much below 10 nanoamps, 10 nanowatts, but 60 and 85 are coming because they are losses, they are switching losses. That happens only when the system is switching. This is a startup with PV. You can see that under voltage lockout is used here. You can see the VD rises. Whenever it goes high, the VD okay goes high, but while falling down, when it becomes below 160 millivolts from where it stop, again it goes low. So you can see that charging, that UVLO comparator what we have used, actually seen in the laboratory how it's working. So when the input voltage is there, output is rising. Whenever it goes above that level, we turn off the harvesting. We don't take any power from the input. Whenever it goes below some level, again we start harvesting. So whether VD okay or not, the VD is enough means you don't harvest any power. VD is low means you harvest power. This can be seen from this block. And we can also start from the RF and PV, which is faster. You can see that it charges much faster. These are the bunch of efficiencies of this system. You can see that the efficiency is more than 80% in reasonable cases. And as a function of the temperature, you see, as we saw that these blocks are consuming very, very low current at such a slow value, there will be leakage of the other nodes may dominate, and efficiency, whether we are not sure in the laboratory it works or not. That's why as a function of the temperature, at different power input power availables, we simulated, we measured the efficiency. We can see that the system can even harvest from 20 nanowatts of power from these graphs. And if you see this last graph as a function of temperature at 3 different input powers, we calculated the efficiency, which is much above 80%. This is how much power do we really save with the help of the comparator and with respect to the oscillator. So efficiency with oscillator is much better than with comparator. So these are the two inductor waveforms to show how we are generating those energized and dump pulses. They actually match with what we calculate. That's what it shows. So as a comparison table, you can see that this paper was published in Journal of Solid State Circuits. It has efficiency at 90% at minus 35 degrees. And even you are at high temperature, it has a reasonably good efficiency for an available power of 1 microwatt. There's a couple of references. I can share these slides. You can go through them. Thank you. If you have any comments or questions, you can ask now. Hello? I'm done with the presentation. If you have some questions.
Mm,
Yeah. No comments, no questions.
If anyone has any questions, please ask. Sir is waiting for questions. Otherwise, we will move forward.
Yeah, I think I'm done for the day. Tomorrow, Priya will discuss some more concepts. Yes.
Okay.
See, I'm pretty sure you may not be following everything, but I can share with you the reference papers and the slides. You can go through them leisurely. But you should get an idea that you can actually design the circuits even with leakage currents and get something done, get something working.
Okay. Thank you, sir, for sharing your practical knowledge on the implementation of various circuits used in the mixed signal design, such as under voltage lockout comparators and DC to DC converters. And I hope all the participants have benefited from your knowledge. Thank you, sir.
Yeah, see, I don't expect you to follow everything, but you should get an idea that things can be done and there's a direction to look at the things. That I think if you can get idea, that's great.
Yes,
Okay.
sir, definitely. Most of the people have gained the implementation of system level implementation.
Thank you.
Thank you, sir.
If there are no
Thank you
further
for-
questions, then we log out.
Thank you for accepting our invitation and joining us. Thank you, sir.
Yeah, sure. Okay, shall we leave or you have some comments, questions? We have how much time? We have a few minutes left still if you want. 2 minutes. Whatever time you want, I'm here, of course.
No problem, sir. Okay, sir. we will wind up the session, sir.
Okay, thank you. Thank you.
Thank you, sir.